All right. Yeah, so that's yeah, thanks a lot for having me. It's great to be part of this nice event. So my name is Andrea Coladangelo. I am currently a postdoc at UC Berkeley and Simon's Institute for the Theory of Computing. I'm also co-founder of qBraid. And so I will be broadly discussing applications of quantum information in the domain of cryptography. So let me start with the question, what is quantum cryptography? So, well, this is cryptography in a world that is quantum. So a world where quantum information exists. And I will tell you in a moment what I mean by quantum information and what properties of it are relevant to cryptography. And so I want to first address some common misconceptions about quantum cryptography. So the first misconception is that quantum cryptography is all about breaking today's encryption schemes. So as you know, Shor's algorithm for factoring can be used to efficiently break most of the cryptographic schemes that we employ today. So this is, bad news. And it's somewhat of an unfortunate, I would say, historic coincidence that we have actually based the security of most of the cryptography that we use today on the hardness of a problem that actually can be solved efficiently on a quantum computer. And so while Shor's algorithm is certainly relevant to cryptography, to quantum cryptography, my message is this is not what cryptography is about. Right? Cryptography's overarching goal is to construct secure cryptographic schemes, not to break them, right? So this is the first misconception. So the second misconception is that in order to make our crypto systems secure against quantum computers, we actually need to actively use quantum information. And so this is not true, or at least we don't believe that this is the case. In fact, all of the cryptographic tasks that we love and that currently rely on unsafe computational assumptions, well, we also know how to construct these with security based on other computational problems, which we believe to be hard for, also for quantum computers. And so in other words, we can fix our current crypto systems without actually using any quantum information at all. So just by basing security on different problems. So then the question is, well, what is quantum cryptography about then? And the main takeaway that I have for you in this talk, if you're taking away just one thing, is that it turns out that quantum information can be leveraged to realize cryptographic tasks that are impossible to realize classically, or to realize them with better security or from weaker assumptions. So actually, quantum information allows us to do even more, than what we can do classically. And so what is it that makes quantum information so special for cryptography? It is mostly two properties. One is the no cloning theorem, and the second is entanglement. And so in the rest of the talk, my goal is to illustrate how these two properties can play a role. So let me start from the no cloning theorem. So what does the no cloning theorem say? So this is something that can be derived straightforwardly from the laws of quantum mechanics. It's basically a consequence of the uncertainty principle. And it says that quantum information cannot be generically copied. So what I mean by this is that, classically given a string of bits, it is always possible to make two copies of it. Right? And essentially this is because one can always read a string without actually disturbing it. Now, on the other hand, quantumly, there does not exist a universal copying procedure that takes as input an arbitrary, unknown quantum state and outputs two copies of it. So quantum information is very different in this regard. And now, on the one hand, this no cloning theorem is bad news. It says that, really fundamentally, it is hard to store quantum information. right? However, on the positive side, in a cryptographic setting, the no cloning theorem actually significantly restricts the possible attacks of a malicious adversary, because the adversary itself cannot copy information. And so the goal for the next few slides is to show you how, we can leverage this no cloning principle in some actual protocols. And so before I do this, I do want to summarize some of the properties of qubits or quantum states that are relevant. And, this is at the cost maybe of telling you some things that you already know, but, I'd rather we all be on the same page. So, as you know, the analog of a classical bit, you will have heard, also in other talks during the day, is a qubit, which can be in a superposition of 0 and 1. And here, alpha and beta are complex numbers. You should really think of the state of a qubit as a vector in 2 dimensions. So think of the 2-dimensional plane with 0 pointing upwards and 1 pointing to the right, for example. And so any combination of the two is also a valid qubit state. And you can think of 0 and 1 as the two, the x and the y axis, if you will. So any combination is also a valid state. So for example, one can have the state 1 over square root of 2, 0, plus 1 over square root of 2, 1, which you can think of as a vector pointing to the 45-degree angle. Or you could have the same state, but with a minus sign, which would correspond to a minus 45-degree angle. And now, one very important property of quantum states is that the only way to actually extract classical information from a qubit, from a quantum state, is by making a measurement. So, for example, you're allowed to ask the question, is the qubit in the state 0 or 1? And if you do so, you will get an answer, 0 or 1. Now, the crucial point is that as a result of this measurement, the state actually collapses to either 0 or 1, with probabilities that depend on the alpha and the beta. So essentially, after the measurement, you may no longer have the state that you started with. This is very different from the classical case, where essentially we're working with the same fixed basis in the classical case, in the classical world. Now, of course, there is, in the quantum world, there's nothing special about this particular choice of axis that we made, upwards and pointing to the right. In fact, you can ask the same question, you can make the same measurement with respect to any other basis of your choice. And by the way, when I say basis, I mean, I'm saying this, the choice of axis. Okay, so you can pick any other choice of axis, for example, the pair of axes pointing to the 45-degree angle and the minus 45-degree angle. And if you ask the question, are you 0 or 1, then the post-measurement state will be one of those two vectors. So there's nothing special about any particular set of axes that we pick. And so here is an example of how we can leverage all of this. So we will, so this is, so we will consider the cryptographic task of key distribution. So this is a simple cryptographic task. There are two parties, Alice and Bob, and they share a simple goal, which is to share a uniformly random secret key. So this is a key that should be uniformly random and known only to the two of them. Now, why would they want to do this? Well, because once they have a random secret key that is only known to the two of them, then they can use this to communicate in a way that is unconditionally secure. So in a way that just cannot be hacked at all. And so the difficulty is sharing the key without actually having to meet in person. And so they would like to achieve this goal of sharing a key by communicating over a public channel. So public here means that any adversary, Eve, can eavesdrop on the communication, can intercept the messages as they are sent along the channel. So now, if you stop and think about this for a moment, you will find that this is actually a very difficult task to achieve if we let Eve intercept any message. And In fact, key distribution is impossible to achieve in the classical world if we want this unconditional security. So unconditional security means the protocol is secure even against a computationally unbounded Eve. Okay. And so this impossibility is quite easy to see. So let's first consider the following trivial protocol, where Alice simply samples the secret key on her own and sends it to Bob, in the clear, bit by bit. So, Alice is sampling the secret key on her own, sending the bits to Bob. By hypothesis, Eve can intercept any bit on the way from Alice to Bob, just like so. And so, Eve can, of course, read all of the communication. So in this case, the key is clearly not secret. Obviously, you have to try something a little bit less naive. So what about more complicated protocols? Well, unfortunately, no matter what the protocol is that you choose, the view of Bob here, you can convince yourself the view of Bob is exactly the same as the view of Eve. Okay, and same for Alice. So information theoretically, if Bob is supposed to learn a key, then so can Eve, right? Because they see exactly the same information. There is no asymmetry at all between them. So this is why key distribution with unconditional security is just impossible to achieve classically. And really the implicit fact that we're using here to argue this is that classically Eve can read all of the public communication without disturbing it, which sounds obvious, but actually this is not the case in the quantum world, right? And so things are different in the quantum world. I won't describe a full protocol here, but I just want to tell you the essence of how things are different. So, suppose that instead, in the quantum world, Alice doesn't just send bits to Bob. She can send qubits. And suppose that she's sending qubits either in the standard basis, so 0 or 1, or qubits in the 45-degree basis, like here, for example. And so let's say that Alice chooses the basis uniformly at random for each qubit. Now, of course, Eve can still intercept the qubit sent from Alice to Bob, and she can try to extract some information from it by making a measurement, for example. However, because she does not know what basis Alice chose, the 0, 1 or the tilted basis, Eve's measurement will be in an incorrect basis at least half of the time. And so therefore, if she picks the wrong basis to measure, she'll disturb the state of the qubit on its way from Alice to Bob. And so crucially, by revealing the choice of basis to each other in a subsequent step, Alice and Bob are able to actually detect with high probability if Eve tampered with let's say with a significant enough fraction of qubits. And so this is really the key idea. Alice and Bob can detect if tampering occurred. If they detect tampering, they abort the protocol. Otherwise, they're confident that Eve did not gain any information from the qubits passing along. And so one can use this idea to obtain a protocol for key distribution with unconditional security, actually, in the quantum world. And this is something that was known already in 1984 from a protocol of Bennett and Brassard. So there's a stark contrast between the quantum and the classical world for this particular task. Now, it's worth pointing out that if we're actually satisfied with security against efficient, so computationally bounded adversary, so not unconditional security, but let's say security as long as you don't have like a super huge quantum, a super huge classical computer or even quantum, you don't run it for like 1,000 years. So let's say we're satisfied with such a security, then we do have classical protocols for key distribution whose security is based on the assumed hardness of certain computational problems, like for example, calculating a discrete logarithm, or other problems like factoring, for example. So key distribution is possible classically, just not with unconditional security. And so a natural question is, well, can we actually use quantum information to realize cryptographic tasks that are, not possible to realize at all classically, not even under, computational assumptions? And the answer is, very interestingly, is yes. And I will show you one simple example, which is quantum money. So this is a Qt application that is particularly suited for the no cloning theorem you'll find. So the idea of a quantum money scheme is to leverage the no cloning theorem to create banknotes that are impossible to counterfeit. So where this inability of an adversary to counterfeit the banknotes is guaranteed by the laws of physics. So essentially, in a quantum money scheme, a banknote is a quantum state, okay? And there is a bank that generates these banknotes, and these are handed to parties like Alice. And so by the no cloning theorem, these banknotes cannot be generically copied. This is the basic idea. So here's an example of a simple quantum money scheme. So a banknote will consist of a number of qubits, okay, where each qubit is in one of the 4 states that we introduced earlier. So, 0, 1, 45, minus 45. And to generate a banknote, the bank simply creates a bunch of such states where each one is uniformly at random in one of the 4 states. And now for each of these generated banknotes, the bank saves this information in some database. So it saves the choice that it made, the choice of bases it made for each qubit, and whether it's up, right, 45 or minus 45. And let's say it assigns this information some classical serial number so that it can retrieve it later in its database. Now, what does Alice do to spend the banknote, or rather to redeem the banknote? Well, Alice can simply return the banknote to the bank together with its serial number. The bank looks up in their database for the choices that they made. The bank then measures each qubit in the banknote in the correct basis and checks that it obtains the correct outcome. And if this is the case, it accepts the banknote, otherwise it rejects. So essentially, if Alice honestly returns the banknote that she received, the verification procedure will pass. And now, how is security defined? Well, informally, we want to say that it is not possible for an adversary who receives 1 valid banknote to produce 2 copies of it, which are both simultaneously accepted by the bank. So this banknote cannot be redeemed or spent twice, except with very small probability. And so what is the intuition for security here? Well, first of all, we know that Alice cannot simply copy the state of the qubits that she receives. This is by the no cloning theorem. So what else could she try to do? Well, she could try to measure them to gain some information about the choices that are made by the bank. However, crucially, Alice does not know the basis choices made by the bank. And so the intuition here is that similarly as in the key distribution protocol, measuring a qubit in the wrong basis destroys information about the state. And so intuitively, if Alice tries to measure all of the qubits in the banknote, she will measure about half of them in an incorrect basis. And so when she returns the state to the bank, approximately half of the qubits are no longer in the original state. And so she would fail with high probability. So this is one example of something that is just impossible to do classically, because any string of bits can just be copied. So there are actually many more applications of quantum information to tasks that are actually entirely impossible classically as well. So some examples here are copy protection of software, true certifiable randomness, one-time signature tokens. Now, I don't have time here to touch upon this. What I want to do instead is to switch gears a little bit. At the start, I mentioned that there were two ingredients that make quantum information special for cryptography. We talked about the no cloning theorem. The second one was entanglement, which I want to discuss next. And so in order to do this, let's return to our example of key distribution. So recall that in key distribution, Alice and Bob's goal was to share a uniformly random secret key. What we saw earlier is that Alice and Bob can achieve this by exchanging quantum information. Now, what I showed you, of course, was a bit of an abstraction of what happens in the real world, because in the real world, Alice, does not create the quantum states out of thin air, right? But she's using some quantum device, right? Some box that produces these states. In particular, Alice, the end user, is a classical being who does not really understand the inner workings of her device necessarily. She's basically just reading, some instructions, manual, and pressing buttons on the device, right? So for all she knows, the device might not actually look like this inside, where this star here represents a nice quantum state, but it might actually look instead something like this. And you see, this is a legitimate concern, especially in a cryptographic setting. The quantum device that Alice is using may have not been manufactured honestly, right? It might have been manufactured maliciously, right? And even if it wasn't designed intentionally maliciously, and it does not have like a monkey inside, it could still be faulty. And so it becomes essential that Alice and Bob have access to some sort of certification procedure for their devices. And so here's where entanglement plays a role in a surprising way. So it's a bit difficult to describe what entanglement is in words. So I'll describe instead, what entanglement can do for us. Okay, so this will be through the lens of a game called the Magic Square game. So in this game, Alice and Bob are playing cooperatively. The game consists of a one-round interaction between Alice and Bob and a referee who is asking classical questions to each of Alice and Bob and receiving some answers in return. So Alice and Bob win the game if the questions and answers satisfy some pre-established condition. And the catch in this game is that Alice and Bob cannot communicate with each other. So in particular, Alice does not know what question the referee asked to Bob and vice versa. So Alice and Bob can talk as much as they want before the game starts, but once they're separated, they can't communicate anymore. So this is the setting. So here's an example of such a game. The referee samples uniformly at random one of the columns of this 3x3 square, and she asks Alice to return a value, 0 or 1, for each entry in the column. So the column is the question, and these 3 bits are Alice's answer. And the constraint that these entries should satisfy is that the parity of the sum of the entries should be odd. Okay. Now for Bob, the referee will instead sample uniformly at random one of the rows of this square and will ask Bob to return the entries for that row. And now the constraint that this entry should satisfy is that the parity of the sum should be even. So odd for Alice and even for Bob. Now Alice and Bob can return whatever answers they want, right? But they should, when I say they should satisfy this constraint, I mean is that they should satisfy it if they want to win the game. Okay. Now there's a final constraint, which is that Alice and Bob's answers should be consistent on whichever entry the row and the column overlap. So in this case, the row and the column overlap in the middle entry, and so Alice and Bob should be responding with the same bit for this entry. So Alice and Bob win the game if their answers satisfy all of these 3 constraints simultaneously. So this is a simple, very simple game that Alice and Bob are trying to win together. Now, assume that the referee is sampling one of the 9 possible questions uniformly at random. Well, then, the question is, what is the best winning probability that Alice and Bob can achieve? In particular, can they win perfectly? And so the difficulty here, of course, is that Alice does not know what question is being asked to Bob and vice versa. So if they want to win perfectly, one thing to note for sure is that they should at least be consistent on their answers. And so it's not too difficult to see that this essentially, forces Alice and Bob, if they want to win perfectly, to agree on some fixed 3x3 square beforehand. So agree to a fixed assignment, to all of the entries of the square, and answer using the entries of this fixed 3x3 square. So certainly, if they do this, they will always satisfy the consistency constraint. But what about the parity constraint? So if you think about it a bit more, you follow along this train of thought, you can see that the question of whether Alice and Bob can win the game perfectly, actually, it boils down to the question of whether there exists a 3x3 square that satisfies all of the parity constraints, so even rows and odd columns. And we call such a square a magic square, so hence the name of the game. And so the question is, does such a square exist? Now, usually I would ask this question to the audience, but in this case, since there are many of you, I will just tell you. So it turns out that such a square does not exist. Okay, and so the way to see this is that if such a square existed, then we could sum all of the 9 entries of the square row by row, and we would deduce that the sum of the parity of all the entries is odd plus odd plus odd, which is odd. If we instead sum the entries, the 9 entries column by column, we would deduce that the parity is even plus even plus even, which is even. And so this gives us a contradiction. So such a square does not exist. And so any strategy that Alice and Bob play will fail on at least 1 out of the 9 possible questions. And so the best winning probability for them is 8/9. And so the surprising part is that it turns out that if Alice and Bob share a pair of entangled qubits, then they can actually beat this 8/9. They can win the game with probability 1. And so this is truly remarkable. What I want to point out is that the game has not changed. It's exactly the same game. Alice and Bob are still non-communicating. So sharing a pair of qubits does not allow you to communicate. Now, Alice and Bob can achieve this perfect winning probability by sharing a very special state, which is known as the EPR pair. So the EPR pair is a state of 2 qubits, which you should think of as one being held by Alice and the other by Bob. And so these 2 qubits are said to be maximally entangled. What this means, in essence, is that no matter what basis you pick to measure each qubit, as long as Alice and Bob measure in the same basis, then they will get the same exact outcome with probability 1. In particular, they obtain either both 0 or they both obtain a 1 with 50-50 probability. So I realize that I'm almost out of time, so I'll try to wrap up in a couple minutes. So what consequences does this have for the question that we asked earlier, which was, how can Alice and Bob certify that their quantum devices are truly quantum and that they're doing what they're supposed to do? Well, if you think about it, this magic square game gives us a way to detect the presence of entanglement, right? So how does it do that? Well, suppose Alice and Bob each have one device and that, these devices are allegedly sharing some entangled state. Well, then what Alice and Bob can do is make their devices play the magic square game, right? They each pick uniformly random questions for their devices, they get answers, and after the game ends, they talk to each other and they just check whether the games were won or not. So they can repeat this process many times. If they observe that the 2 devices win with a fraction noticeably higher than 8/9 of the times, then they are statistically confident that there was indeed some entanglement between the two devices. So despite being classical, and this is the remarkable part, Alice and Bob, they're able to certify the presence of genuine quantumness. And so there's one additional fact, which turns out to be very useful, which is that, you know, one can not only certify the presence of entanglement, but one is able to make an even more precise statement. So in fact, it turns out that, and this can be shown mathematically, it turns out that there is actually a unique quantum state that allows the two devices to win with probability 1. And this state is the EPR pair. So not only can Alice and Bob certify the presence of entanglement, but if they actually observe that the two devices win all the time, then they have some statistical confidence that the joint state was most likely an EPR pair, right? So no other state could have produced a perfect winning probability. And so I guess the last thing is that I want to say is, I won't go through this for much longer, but you can use this certification idea using the magic square game within a key distribution protocol. So essentially, Alice and Bob can test some of their EPR pairs during a key distribution protocol, and they do not have to trust that they were manufactured correctly. Okay. So I'll skip this. And yeah, the last thing I want to say, other than thank you, is that actually some of these experiments where you're making spatially separated devices play something like a magic square game, they're actually being carried out. They're quite advanced nowadays. They're being carried out in various places in the world. And so some of these key distribution protocols are actually, you know, coming to practice, which is very nice. Thank you.
Thank you, Andrea. And as a reminder to everyone, you can submit some questions in the Q&A to be answered. First question from my end is, where do you see the first applications coming in? I know you used an example from finance, but where do you think kind of the most important industries or specific problems that will be addressed by this cryptography?
Yeah, I think so. The first applications that we will see, and this is something that other governments around the world are investing heavily in, is probably this key distribution that I talked about. So allowing two parties to share uniformly random secret key that then allows them to communicate in a way that is unhackable, essentially. And these experiments are being carried out. I guess I didn't have so much time to talk about it, but you can use these EPR pairs within a protocol to achieve key distribution, and governments like China, the US are exploring the possibility of having these EPR pairs being sort of shipped to Alice and Bob from a satellite. So one qubit goes to Alice, one goes to Bob, and they're sort of sent from some satellite. So there's a lot of work being put into this. I think this is the first thing that we'll see, because I mean the sort of technological requirements for this are not as heavy as for some other quantum computing applications. So for instance, as you saw, this key distribution protocol was very simple. It only involved 4 different states, right? I didn't talk about quantum gates. It was just literally those 4 states. You don't even have to store them for a very long time. You just prepare them, you send them to the other party. So there's not even much of a quantum memory involved. So actually technologically, this is one of the least demanding things. It doesn't require universal quantum computer or anything like that. Yeah.
So would you see something like this being a blended approach or supplanting blockchain when it comes to just that's where I'm trying to understand a little bit more that from the security perspective, but to your just previous statement about it being a temporary state, where, once these communications happen, is there an assumption there's not a transactional log of it, or?
So if I guess if you talk about blockchain, that's like one particular application of many of this, simpler, more basic primitives. It's blockchain is like a much more complex application with several different parts. There are signatures, various other things. But if you're talking just about whether we'll replace the current encryption schemes that we use now, based on factoring or other assumptions, with something like key distribution, which is unconditionally secure, I think that I don't think that in the near future, we will have a replacement. It will be most likely be blended in. If we have sufficient control on the technology that we can actually make this available to regular users, it will be definitely more blended in. At least that's what I think. Most likely this unconditional security may be something that governments or high kind of in settings where you demand very high security. So I guess one difference that I didn't touch upon is like, nowadays pretty much all of the cryptography that we use does not have unconditional security. So if you have a computer that is big enough, okay, in principle you can hack all of it. And for instance, if you have a quantum computer, you could actually already hack a lot of the cryptography that we use today. So what people, the reason why people trust it is because, with the best algorithms that we know nowadays, it would take, thousands of years for even the best classical supercomputer to break the cryptography that we're using today. So people are fine with that. But one concern is maybe 30 years or 50 years, 100 years from now, we will actually have, even forget about quantum computing, we may even have a classical computer that is much more powerful than the ones that we have today. And actually, you can, if you have stored all of this in, ciphertext from today, you can go back and break all of them, 50 years from now, and then see what people talked about. So if you're in a setting where you worry about this retroactive security, then you have to use you have to use things that are unconditionally secure, and essentially, yeah, only quantum information gives you such a security. So that's one I guess practical reason to elect to use one other than the other. For most regular users, we don't care 100 years from now if people come and look at our conversations, but perhaps for the government, and who knows, maybe it's not 100 years, maybe it's like 15 or 20, right? And so maybe then that starts to become more of a concern.
Great, thanks for that.
Yeah.
Looking at some of the questions that are coming in from our Q&A, here's a question that I might need some clarification on because I think you might have addressed it, but I think the question is, who has demonstrated the most impressive real-world key distribution exercise to date, in your opinion? Would it be the aforementioned governments, or has there been some sort of example that you think beyond the magic game?
Actually, I don't know the answer to that off the top of my head, so you can probably Google this. But I think that probably in China, actually, for some reason, they're investing more heavily on, relatively speaking, on this compared to, I think that in the US, there's a big focus, and in other parts, there's a big focus on building, universal quantum computer. For some reason, in China, the direction, or there was relatively more focus on key distribution from the get-go. So I would expect that it's from there, but I don't know off the top of my head.
So maybe stepping back a little bit with a question, what drives you in your pursuit of this research? Like what is it that you see being some of the applications of some of the things that you're working on? Yeah, beyond qBraid.
Yeah, for me, I think quantum cryptography has a lot of elements that are very fascinating to me, and I think what drew me to it in the first place is that there are some very fundamental facts about nature that are very counterintuitive to what what we actually experience every day, like the no cloning theorem, for example, or some of the consequences that we saw for entanglement. And these are really very fundamental facts. And moreover, you can do sort of some very interesting mathematics, which I've always liked mathematics, and you can do some very interesting mathematics and actually use these very fundamental facts to build at least proof of concept or some sort of applications that actually have it's not about the fact that whether they will be one day practical or not, but you can actually build something that has a connection to the real world, like a cryptographic application, right? From something that you didn't even think that was how the world behaved. Somehow you can even, not only it's so counterintuitive, you can even use it to do something that you thought was impossible before. So I think this whole, all of these ingredients make for something very, very interesting.
We have another question that maybe you know the answer to, but what, in your opinion, I guess, or more objectively, are the institutes that have the most effective ongoing research in this area of quantum?
So I think maybe I can speak on the theory side, because that's what I work on. On the theory side, there are many great places. There's the usual suspect, UC Berkeley, MIT. There's a big group in the University of Maryland. There's the Institute for Quantum Computing in Waterloo. Caltech obviously also has a big group. So yeah, there are a few. I think, and there are some groups in Europe as well. And yeah, actually, the good sign is that many of this, many universities actually, there seems to be desire to expand the efforts in quantum computing. Even not only on the industry side, but also in academia. That's a good sign.
Thanks. Well, knowing that we're approaching the wrap up, we'll maybe end with an easy question for you, as we've had a question from the audience about what the actual building and location is on your final slide.
Oh yeah, I meant to say it. This is actually in the Netherlands. So this is something that was done at TU Delft in the Netherlands. Yeah, so they had, I think, the first loophole-free, whatever that means, demonstration of of winning something like the Magic Square game, and they did this by having essentially being able to share entangled pairs over a large distance. So this is what you're seeing here.
Cool. Well, like I said, thanks again for a great presentation.
Thank you very much.
Yeah, we appreciate it. And yeah, look forward to hopefully seeing what the next evolution of things are in cryptography as we try to plan more events around this. So appreciate all the info.
Thanks.
Thanks. Have a good one, Andrea.
Mhm.